So we started section 1.2 last time. We'll finish it today. And we're taking a look at patterns. In particular, we saw a lot of things with geometric and arithmetic patterns. And I mentioned, actually, that I wanted to show you one other thing, and we'll do this before we get to our next example, which is example number 3. I wanted to show you that when you have a pattern that you don't recognize what it's doing, which is what we had happen here on B, there are sometimes other ways that the patterns can behave. Now, crazy enough, my children brought home geometry homework yesterday, and they were doing some stuff with patterns, and they had yet another kind of a pattern going on. I'm not going to talk about their pattern, but I will talk about how this one works, because there is a very distinct way to do this that's pretty consistent with the kinds of questions you guys will see. So I want us to take just these numbers right here, and we know that they came from this sort of expression. We know that. But I just wanted to take those numbers and to show you how you can figure out without n squared minus 1 what would have come next. Okay? So I'm going to go to another screen. We're going to put in 0, 3, 8, 15, and 24. So I have 0, 3, 8, 15, and 24. I'm going to space them out. All right, so I want you to think about this like addition. Okay? What would I have, because multiplication doesn't stand a chance because I've got a 0 on the list, so it wouldn't work anyway. If I were to go from 0 to 3, what would I have to add? 3. Yeah. And 3 to 8, what would I have to add? 5. And 8 to 15?
7.
And 15 to 24? 9. Do you see a pattern? What would I have to add to get the next one? 11. Okay? And if you don't recognize it yet, you could actually go a step further. You could actually take a look at how do I get from 3 to 5?
2.
I add 2. And from 5 to 7? Plus 2. 7 to 9? Plus 2. So in this particular one, what you're seeing is something called a common second difference. The first differences are the ones that are going from 3, 5, 7, to 9. They don't match. But the second one has a common or the same second difference in the problem. Now, some of our problems will not do it in 2. You might actually have to go 3 layers deep. It would have a common third difference. But if you didn't recognize that this was plus 11, you could then add plus 2 here, which would give you the plus 11. And then you could add your 11 to your 24, and you would be at 35, and you could keep going. Okay? So this is another way to do patterns, and it actually happens when things are squared. And that's actually why the second differences are happening, is because they're squared general formulas. But anyway, I wanted to draw your attention to that. Okay, let's go back to example number 3 then. And we're going to look at counterexamples. So what is a counterexample? So we talked about this, I think it was last class period, we had a definition. Counterexample is an example that shows something is false. And all you need is one counterexample to say that it doesn't work for every number, because you found one that it didn't work for. So if you take a look at this, we have a statement made by a student, most likely, that says that if we have n plus 5 and we divide by 5, we get n plus 1. Okay? Counterexample means they're telling you there's going to be one, means they're telling you this is false. And they just want you to find a number for n that proves that it's false. A number for which this does not work. So what number for n, we got lots of them that will be false, make it false here. What number for n would you like to try?
2.
2. Okay, so n equals to 2. Sorry about that. We can check 2 plus 5 over 5. And I'm going to put a question mark in between. Is this equal to 2 plus 1? So on the left, I get 7 over 5. On the right, I get 3. Does 7 over 5 equal 3? No. That means that what we did create was a counterexample. Now, there is always the chance that you randomly pick an n that actually made it work. If that's the case, then you would just need to pause and say, okay, that's not what I was supposed to pick. I need to try something else. Okay? Sometimes there's a lot of numbers that create a counterexample. Sometimes there's only one, and one's all it takes. So you might have to be a little bit more intentional about how you think about the problem in those cases. Now, this kind of an error is really common, by the way. This is the kind of thing that I would expect to see on an algebra assignment, even here at OBU. Maybe even something that would happen in this class if you were moving quickly and things like that. It's a very common error. Why might a student think that you could somehow do this? What do you think they're doing to get n plus 1? Yeah.
I think they probably did 5 divided by 5 is 1.
Yep.
And then that leaves it.
Yeah. So they're dividing, but they're only dividing a portion of it by this value, right? That is what it looks like. It looks like they're just dividing the 5 on the end, or what they're even potentially doing is something like this, where they mark it out. This is probably how their work would look if they showed work, and they would end up with a 1 right here. They might even end up with a 0, depending on how they're incorrectly thinking of it. That's also a possibility. So it's really much more helpful if you can look at student work and figure out why might they have come to this conclusion, so that you can address the issue underlying the problem rather than just showing them that it doesn't work. Does that make sense? So what's going on? Well, it's probably something like that. So the student seems to be dividing the 5s, right? But forgetting that n is divided by 5 as well. Now, they could do this division where they have the 5 over there, but if they did, they would, that's a terrible n, let's try it again. They would have to write it like this, right? They can divide the 5 by 5, that gives them 1, but they'd also have to divide the n by 5. That would be a correct interpretation for this. Okay. Figure-it numbers. Figure-it numbers are based on visually geometric patterns. I use the word visually in there because we've got these things called geometric sequences that we just did. That's not what it's talking about. It's not talking about those. They're visually geometric patterns. These examples typically are neither arithmetic or geometric, and such numbers can be represented by dots that are arranged in the shape of those figures. And there's so much overlap in my life, sometimes it's a little bit scary. Like you go, ooh, like what in the world happened? This also showed up on my kids' homework that they brought home from geometry. They had to figure it, they have a diagram. They were looking at patterns is what they were doing, actually, is why this was happening. But they were looking at patterns, and they were looking at these dot patterns too. They were looking at figure-it numbers. I don't think that their book called it that, but that's what they were doing. So triangular numbers, they look like triangles. So the first triangular number is a single dot, but the next one has 3 dots that are put together kind of like this. And then we have this shape showing up. And then there's this shape. My pictures are not perfect, so forgive me about that. I'll do one more. This would be in triangular numbers, okay? Their dots are in the shape of a triangle, specifically an equilateral triangle here. What I'd like for us to look at is the number of dots in each pattern. So how many dots are in the first shape? Well, 1. It's not exciting, like I said. How many dots are in the second shape?
3.
3. How about the third one?
6.
6. The fourth one?
10.
Yep. And then the last one?
So that's 17.
17. I think it's 15. Is it 15?
Yeah,
15? Okay, I think 15.
It is.
Yep. Yeah, so and we can just count them and then being careful or whatever. We can also sort of see what's happening in one way or another. When I visualize these, to me it looks like you're putting another row of dots on the bottom. And so I just add the additional dots. So from here to here, I add 4 more dots on bottom, so there's 4 here. From here to here, I add the 5 more dots on bottom, so there's 5 here. Kind of depends on your perspective. So this is a pattern, numerically, of 1, 3, 6, 10, 15. And I could draw in the next shape. I could do that. Like I would just, like I said, make another layer on the bottom. I could do that. But this also creates a numerical pattern that fits with what we just did a minute ago. If I take this numerical pattern and I take a look at what happens, hang on, to get from one number to the rest, down the list, how do I get from 1 to 3? Well, I'd add 2. How do I get from 3 to 6?
Add 3.
Add 3. 6 to 10?
Add 4.
Add 4. 10 to 15?
Add 5.
Add 5. And we could continue that, right? This has a common second difference because if I did it again, I'd get plus 1s on all of them. Do you see that? So these are called triangular numbers. I'm showing you the two most basic ones in your notes. They're going to give you a little bit variations of these things too in your homework. The next one that we're going to look at is going to be square numbers. So what do you think the shape of these are going to be? Squares, you got it. And it's going to start with the very unexciting single dot just like before. And then we're going to do these dots like this. My squares are going to look a little more rectangular in shape because I have a difficult time getting them to draw the way I want them to sometimes, but that's okay. We'll see what I can do. It's probably not going to be any better. I think that one might have been better. That looks pretty square. Okay, I'll do one more. I say that. Pictures get a little sloppier as they go, but they're not bad. All right, so if I'm looking at these dots, the way that they're drawn, and I'm doing the same thing I did in the last one where I'm counting the number of dots. How many dots are there in the first shape?
Just 1.
1. Second one?
4.
Third one? 9. And then 16. What's the last one? 25. So I have 1, 4, 9, 16, 25. There's 2 different ways you can think about this pattern. Does anybody recognize what these numbers are? They're squared numbers, right? That should make sense, right? The image is a square. I got that, right? So this is 1 squared and 2 squared and 3 squared and 4 squared and 5 squared. And we could actually write a formula for that. It'd be pretty nice. We write n squared, right? We're not going to be asked to do that, but it is a pretty nice, compact, simple one. But there's also that same second differences situation that we had before. So if I won't go from 1 to 4, I'm adding 3. 4 to 9, I'm adding 5, 7, and 9. And if I do it one more time, I have common second differences, right? So another way to see it. Yep.
So if it's asking for the nth term in something like this,
It won't. It won't ask for that. Yeah, it's not going to ask for the nth term on these because the only ones that we can do the nth term on for the ones we've learned and the ones we're going to learn are arithmetic and geometric, and these aren't them. So it won't ask for that.
On number 3B, maybe I'm just reading it wrong, but I thought that's what it was asking.
Okay.
because-
We can look at it later, but
Okay.
it's not.
Okay.
It's not what you're interpreting because it won't do that.
Gotcha.
Yeah. Okay. I think there's something else. One more. Oh, yes. Okay, this actually happened. Man, I really feel like I should take the date out at this point because you guys were like 8 or something. But it really did happen. Oh, fun fact. One of the teachers of my children actually took this class in 2013. And I didn't remember her name, but she's changed. She's gotten married. But so I got to meet her yesterday. But yeah. So 2011, this happened. We created a college at that time called the College of Science and Math. The school has restructured a couple times since then, so now we're called the School of Science and Math, but it was called this. It's the James E. Hurley College of Science and Math. So James E. Hurley, if you were in chapel this morning, you heard his name mentioned. Were you in chapel this morning? It's the prayer that Dr. Westbrook read from the book. That's him. So he was a mathematician, actually. And the dean at that time, her name is Dr. Bosch, wrote this expression on the board. She wrote a 3 and then a decimal and then 1, 4, and 1, 5. And she asked us to find the next 2 digits. Do not say anything out loud. I would like for you to write down what you think the next 2 digits should be in this sequence. Okay? What's next? Jot down your thoughts. There are two popular answers. So somebody tell me what you wrote.
1/6.
1/6. Who wrote 1/6? It's a very popular answer. Got about half the class wrote 1/6. Somebody tell me if you didn't get 1/6, what'd you get? 9/2. How many of you wrote 9/2? Don't talk about the Y's. I just want hands up. Okay. The 1/6 people are looking at the 9/2 people and saying, what are you talking about? The room in which this was given was a room full of science and math people. And we all wrote 9/2. Every single one of us. So, somebody who wrote 9/2, why did you write 9/2? It's the next numbers in the value expression of pi. That's why we did it. We're just going to like a bunch of math and science people. They wrote this on the board. Dr. Bosch wrote this on the board. And we all looked at it and was like, it's 9/2. Why are you asking us such a silly question? And those of you who wrote 1/6 did the same thing. It's 1/6. Why are you asking us such a silly question? It seemed obvious to us. Our perspectives were different, right? So in that room, all the math and science people saw pi. And some of you did as well. But a lot of you also saw 1/6 because it looks more like some of the other things that we've done in the last day and a half, right? It looked like those kinds of patterns. So the question is, which one's right? And the answer is both. So the question down here actually talks about what we did in this activity is called inductive reasoning. You used some sort of a prior experience and you used the initial part of, in this case, a pattern, and you made a prediction on what was going to happen next. And we got different predictions based on what was going to happen next. What does this tell you about inductive reasoning? Well, it doesn't always lead to the same conclusions, right? Sometimes it will lead us all to the same conclusion and we're all right and that's good. And sometimes it will lead us to different conclusions and there's just not a right answer. So inductive reasoning can yield different values. So there may be more than one legitimate generalization. Both of these are legitimate generalizations of what would we think is happening next. Yeah, crazy stuff.